Imagine you've got a super laser, one so powerful it can watch electrons dance. But it's got a tiny problem. It needs glasses. Today, we're going to look at how scientists are teaching an AI to be its own personal optometrist, and how that's unlocking some seriously next-level science.
So to really get why this is such a big deal, let's just start with this question. What if you could take a particle accelerator that's miles long and shrink the whole thing down to fit on a lab bench? It sounds like something straight out of a movie, right? Well, that's the incredible promise of the tech we're diving into today.
The magic behind this is a process called high harmonic generation, or HHG. Basically, you blast a super intense laser at a target, usually a gas, and it kind of supercharges the light, converting it into much, much higher frequencies. We're talking all the way up into the X-ray part of the spectrum. And just like that, your tabletop setup becomes a powerful X-ray source, something that used to require a massive facility the size of a stadium.
So how in the world does that work? It's actually a pretty elegant three-step dance. First, the laser's electric field is so strong it literally rips an electron away from its atom. Second, that same field takes the electron for a wild ride, accelerating it away. And then third, a split second later, the field flips and bam, it slams that electron right back into the atom it came from. This collision releases a burst of high-energy light. You can think of it like using a laser to strike a tiny atomic bell, and the sound it makes is an incredibly high-pitched light wave. And listen, this isn't just some cool physics party trick. These tabletop X-rays are a total game changer for a whole bunch of fields. We're talking about attosecond science. That's studying things that happen on the timescale of a quintillionth of a second. It's just mind-bogglingly fast. This stuff lets us probe new materials, see what's going on inside superhot plasmas, and take imaging to a whole new level of detail.
Okay, so it all sounds amazing. A particle accelerator on a desk? But there's always a but, isn't there? To make any of this work, you need a laser beam that is absolutely perfectly pristine, and that brings us to the big roadblock these researchers were up against. You see, it doesn't matter how perfectly you engineer them. The mirrors, the lenses, everything inside a high-power laser system has these microscopic, unavoidable flaws. They act just like a smudge on a pair of glasses, creating distortions in the light that scientists call aberrations. And for a process as delicate as HHG, these tiny aberrations are a total deal breaker. And this right here shows you the problem perfectly. On the left, that's the dream, a single, razor-sharp, intensely bright point of light. But on the right, that's the reality, a distorted, blurry, splotchy mess. That fuzzy beam just doesn't have the concentrated punch you need to make the whole HHG thing happen. So how do you fix a problem you can't even really see? Well, the first thing you need is a way to describe it. You need a language to talk about these imperfections in light. And that language comes in the form of these mathematical tools called Zernike polynomials. The best way to think of them is like a recipe for blurriness. Each polynomial is a specific ingredient. You got one for being out of focus, one for astigmatism, a dash of something called coma. By mixing these mathematical ingredients in the right amounts, you can perfectly describe any weird, distorted shape the laser beam takes on. Okay, so now you can describe the problem. Great. Now you need a tool to actually fix it. And for that, let me introduce the hero of our story, this thing called a spatial light modulator, or SLM. It's basically a super high-tech programmable screen, but instead of making images, it shapes light. And the way it works is just beautiful. The distorted, messy laser beam comes in and hits the SLM. But the SLM has been programmed with the exact opposite distortion. It's like noise-canceling headphones, but for light. The two opposing patterns meet, they cancel each other out completely, and what comes out the other side is a perfectly flat, corrected beam, ready for action. Which leads us to the million-dollar question. Finding that perfect anti-blur recipe to program into the SLM is a nightmare to do by hand. It could take a scientist hours, maybe even days of tedious tweaking. So how do you find the exact right correction, and how do you do it fast? Well, the answer, as you've probably guessed, is to let an AI do it. So these researchers came up with two different AI strategies to automate the whole process, basically teaching the laser system to focus itself. And you can think of it like an AI showdown. In one corner, we have the detective, a methodical approach called Bayesian optimization. And in the other corner, we have the expert, a quick-draw pattern recognizer called a convolutional neural network, or CNN. So the detective's strategy is like a really smart game of hot or cold. It tweaks a setting, measures if the laser got brighter,
and then uses some pretty clever math to make an educated guess about what to try next. It intelligently searches for the best possible settings. It's thorough, it's smart, but it takes its time.
The expert, the CNN, has a totally different approach. Its goal is pure speed. A CNN is the same kind of AI that your phone uses for facial recognition. The idea here was, what if we train it to recognize blurry laser spots instead of faces? Could it just take one look at the distorted beam and instantly know the exact recipe needed to fix it? And here's the part that really blew my mind. To train this expert AI, they used just 506 images. That's it. In the world of deep learning, where people talk about training on millions or billions of examples, 506 is basically nothing. And that's a really big deal, because it shows that for these specific, well-defined scientific problems, you might not need a massive dataset to get an AI to do something useful. So the methodical detective versus the lightning-fast expert, how'd they do? Let's check the scoreboard.
Well, the CNN, the expert, it was a knockout. When they showed it brand new, completely unseen blurry spots, it predicted the correct fix over 80% of the time. Think about that. From a single picture, it could diagnose the problem and write the right prescription 4 times out of 5, instantly.
And this chart gives us a little more detail. On the data it trained on, basically its open book test, it scored over 92%. That score drops a little on the final exam, the totally new data, down to that 80%. That little gap is a classic sign of something called overfitting, which is expected with a small data set. But let's be real, an 80% on the final is still a fantastic result. So in the end, it's not really about which one is better, they're just different tools. The Bayesian detective is slow and steady, great for fine-tuning. The CNN expert is incredibly fast, but you have to train it first. The real takeaway is that both methods prove that AI is a powerful, effective solution to this really tricky problem. And that brings us to the ultimate payoff. The researchers themselves say it right here. This work paves the way for real-time adaptive systems. We're talking about lasers that can literally watch themselves, see an imperfection start to form, and correct it on the fly, all without a human ever having to touch a thing. So the big picture, the main takeaway, is this. We are moving toward fully automated, self-driving labs. Instead of having brilliant scientists spend their days just tweaking mirrors, an AI can maintain a perfect experiment 24/7. That frees up the humans to do what they do best, focus on the actual discovery. It just makes the whole process of science faster and more powerful. And that leaves us with a pretty fascinating thought to end on. If an AI can learn the subtle language of light and master a tool as complex as this, what other fundamental instruments of science could it learn to operate? What kind of currently impossible experiments suddenly become possible when every lab has an expert AI on the team?